Hello, this is a chemistry video. I am following the order of sections in Brown, Burston, LeMay, and Murphy's chemistry, the central science. We're in chapter 3, which is on stoichiometry, has to do with balancing equations and things like that. And this sixth section in the chapter is the title is at the bottom, quantitative information from balanced equations. But that's very obscure. And so I decided to title this video Grams to Moles and Back. All right, so let's dive right in. So let's say you have some sort of a balanced equation. So we're far enough in the chapter now to where you should know how to balance an equation. Okay, I've got two oxygens here, so I need to have two oxygens here, and so forth. So let's say you've got a balanced equation. Whoa, that's a balanced equation, right? So this is butane, C4H10, in a liquid form. Got two of them. For every 13 oxygens, will yield 8 carbon dioxides and 10 waters. In a gas form, no less, and then oxygen in a gas form, of course, and the carbon dioxide is a gas as well. So butane is the fluid in, if you've got a little lighter, cigarette lighter, that kind of thing. Butane is the gas that does it, the carbon that does it. Okay, so this is a balanced equation. Now, these coefficients, they tell us the relative ratios of, for example, molecules. I need 2 butane molecules and 13 oxygen molecules in order to get 8 carbon dioxide molecules and 10 water vapor molecules, okay? So this works in terms of proportions of molecules. It also works in terms of proportions of moles. So if I have 2 moles of butane and 13 moles of oxygen, I can get 8 moles of carbon dioxide and 10 moles of water vapor. So the balanced equation gives us the proportions between the various entities. Okay, so let's say you've got 1 gram of butane. Got 1 gram of this. So how much CO2 can I get from that? I mean, we could solve for any of them. So if I've got 1 gram of butane, how much hydrogen do I need for this thing to be fully used up? So how many grams of carbon dioxide will I get if I start with 1 gram of butane? How many grams of water vapor will I end up if I start with 1 gram of butane? Okay, so because we know the proportions and some other information, we can solve for that sort of thing. So let's say you've got 1 gram of butane, C4H10. Now the molar mass of butane, we just add up. So the atomic mass of carbon is 12, and the atomic mass of hydrogen is 1, roughly speaking. So 4 times 12 is 48, plus 10 is 58. So the molar mass of 1 butane molecule is there's 58 grams per mole, okay? 58 grams per mole. Now, so I can figure out how many moles of butane I have if I have 1 gram of butane. So 1 gram of butane times 58 grams per mole, or if you flip it, 1 mole per 58 grams, basically we're dividing 1 by 58, right? It's going to be 0.0172 moles of butane in 1 gram, right? Or we could say 1.72 times 10 to the minus 2 power if you wanted to do it that way. That's the way the book does it for this example. Okay, so we figured out how many moles of butane we have if we have 1 gram. So how much CO2 can I get from that? Assuming I have adequate amount of oxygen, if I have 1 gram of butane, how much CO2 can I get out of it? Well, this is how many moles of butane we know. What is the ratio? What is the ratio of butane molecules to carbon dioxide molecules? Or better yet, what is the ratio of butane moles to carbon dioxide moles? Well, it's 2 to 8, or 1 to 4, right? If I simplify, I'm going to need 4 times, I'm going to get 4 times as many moles of carbon dioxide as I have butane, right? 4 times as many. The ratio is 8 carbon dioxides for every 2 butanes. So I'm going to multiply by 4, and so if I multiply this 0.0172 moles by 4, I'm going to get, if this reaction proceeds, I'm going to get 0.0688 moles of carbon dioxide. All right? So now, if I want to know how many grams of carbon dioxide that is, I take 0.0688 moles of carbon dioxide. And then what is the molar mass of carbon dioxide? Well, carbon is 12, oxygen is 16. So I've got 16 times 2 is 32, plus 12 is 44. So there's 44 grams for every mole of carbon dioxide. So the moles are going to cancel out, right? A lot of this is just putting things at the top and the bottom to where they cancel out. So the moles are going to cancel out, and I'm going to be left with grams. Multiply this by this. Voila. If I have 1 gram of butane and it runs its course, I'm going to get 3.03 grams of carbon dioxide. Okay, so here's a chart from the book, which I've drawn out. So no, I don't want to violate copyright, although I'm still showing you the same diagram. But anyway, that's not important right now. So if I have grams of A, butane, for example, I go from grams to moles to grams, right? So I had 1 gram of butane. I used the molar mass of butane to figure out how many moles of butane I have, right? So grams divided by grams per mole is the one way to think of it. And then I use the ratio of the coefficients. Remember, it was 2 to 8. So 4 times as many moles of carbon dioxide for every 1 mole of butane. And so multiply, or whatever you have to do, the ratio of the coefficients. That gives me the moles of the target substance. In this case, it was carbon dioxide. So then I use the molar mass of carbon dioxide to figure out how many grams of it. So if I have moles, then I multiply by grams per mole, and I get grams. So this is the process that you follow. 3-step process to get from the grams of one part of a equation to the other part. By the way, there is a symbol that you might learn from this section. It's not quite an equal sign. It's got the bottom part of an equal sign, but the top part is like a little caret, and it means is stoichiometrically equivalent to. So like 2 moles of butane is stoichiometrically equivalent to 8 moles of carbon dioxide. It's like an equal sign, except the top part, it kind of looks like a corporal insignia in the Army. Got a little hat on the top and then a line at the bottom. Okay, well, this has been how to get from grams to moles to grams and to moles and back in chemistry, in stoichiometry. More videos to come.